this lecture, I will try to introduce the basics of activated sludge modeling, and especially activated sludge model number 1, which is the general model used in, say, the wastewater world for activated sludge modeling. What I will do is briefly go through a range of topics this afternoon. The first part is more introductory. What is a model? Why are models used? And what are some basic aspects of constructing models? Of course, not completely oriented to the fact that you can construct models in the end, but by introducing this, I hope you at least get some background on what models are and how you can use them or judge them. Then I will move to the Iowa activated sludge models, tell a little bit about the history, how has it been developed, what's the background. In extenso, I will deal with how activated sludge model number 1 has been developed, and then finish with a brief overview of other models which are in the literature and put them a little bit relative to ASM1 as in that context. So if we talk about a model, then we have to realize that it's always a simplification. A model will never be exactly like reality. So the question, does this model describe a wastewater treatment plant, is senseless unless you add what parts of the wastewater treatment plant it should describe, because you will never make a model which describes every single organism, every molecule of water, or every detail of the process. You will use a model in a simplification of reality and in such a way that it describes that part of reality which is of relevance to understand and to deal with. And in order to do so, there are two aspects which are very relevant in modeling. One is the aspect of time, and the other one is the aspect of scale. If you look to time, then the important part is that we can, say, separate processes in 3 groups. And we can have processes which are in so-called frozen state. We can have processes in dynamic state, and we can have processes in steady state or equilibrium. The models usually orient to describe the dynamic state, so the state where variation occurs as a function of time. A process in frozen state means that that process will change in time, but not in the time that you are interested for the process. For instance, if you're dealing with daily dynamics at a wastewater treatment plant, then the concentrations of ammonia in the effluent will vary over time, the concentration of nitrate will vary in the reactors, etc., etc. But within that one day, the concentrations in the sludge digester, which is also sometimes part of the total activated sludge model, will not change, because usually there is a hydraulic retention time of 30 days, so the characteristic time of change in a digester is in the order of 2-3 weeks. And you can consider what is happening in the digester as a kind of frozen state. There's hardly any variation if you compare that to the variations in the wastewater treatment plant. At the other side, you have processes that are in a steady state or in equilibrium, and that are very fast processes. These processes go so quick that they go much more quick than the dynamics you're interested in. Again, the changes we talk about usually in wastewater treatment plant are changes in ammonia concentrations in the order of magnitude of hours, process control maybe in the order of magnitude of minutes. But if you talk about chemical equilibrium, so chemical precipitation processes, they will more or less occur instantaneous, in a few seconds even. So these processes you don't need again to describe in a dynamic way, because they go so fast that you can assume that they are in equilibrium or fully performed. So this is the first thing. If you make a model, you think about which processes are of interest, what are the time constants, the time frame, the dynamics of the process, and then you describe very well those processes which are time varying, which you're interested in the dynamics, and the other 2 processes, those in frozen state and steady state, you can usually introduce in a much more quick way or simple way in the process, in the model. or you forget about them because you can use this as a, like for instance a digester, you could use that as a kind of continuous process with all the time the same concentration under certain conditions. So this is the first major issue on trying to simplify the reality. Split in time constants and only look to those processes which have the dynamics in the order of time which you are also interested in. For wastewater treatment, that's usually hourly, daily dynamics, sometimes yearly dynamics, and then of course a digester becomes important. Because over the year the behavior of the digester will change because your sludge production will vary during the year. The second part is space resolution. You can theoretically make a model which describes every micrometer of an activated sludge plant. But the question is whether you're interested in it or not. And that depends on, again, what is the purpose of the model. What are you intending to do with it? If you make a model of the Earth and you fly over it, you're sure that you need not to know every 10-meter difference in altitude on Earth. If you're walking over it, that every 10 meters might mean a lot of difference whether it's really flat or you all the time have to go up and down 10 meters in time it takes you to get somewhere. So the space resolution depends again on what you want and the relevant. And in generally again within wastewater treatment plant we're dealing with reactors in the order of, and so that we deal usually with the scale of several meters we want to describe. We do not want to describe in generally, for instance, if we have a flock inside an activated sludge flock, we will have a gradient of concentrations, and it's possible to describe that, but you will see that in the normal activated sludge modeling, that gradient we neglect, because it's not relevant enough for most cases to take that into account. So we don't describe it at the, say, scale, length scale of an activated sludge flock, but we describe generally things at the length scale of a reactor, which is meters or even tens of meters, depending on the conditions. But these two are very basic. The first things to simplify things, if you start from reality to make a model out of it, realize time variation, realize relevant space. And the third level is relevant detail. You can make and also reasonable well use models which are completely black box. You don't know anything what's going in or what's happening inside the treatment plant. You will only look to the influent. What's inside is one big black box and the effluent. Typical old design methods based on F/M ratios, so based on sludge loading rates, you can consider as a kind of black box. You don't really know what processes go on, but you know if you apply that sludge loading rate, that you can design a wastewater treatment process in a proper way. So the model can work. So a black box model is not by definition wrong or is not by definition not scientific. It depends very much on, again, the purpose. And if the purpose is design of wastewater treatment plant, practice has also showed that F/M ratios can be a very good way to use in your design. Although it doesn't tell you anything about the sludge, it does about the composition of the sludge. So you can refine that, and you can, what has been done in activated sludge model number 1, in this general activated sludge modeling, split up the sludge in relevant fractions. Part of the sludge is just inert organic matter. A part of the sludge are nitrifying bacteria. A part of the sludge are heterotrophic bacteria. A part are maybe denitrifiers or phosphate removing bacteria. But you specify the different functional aspects of the sludge. So you have a kind of population-based model. And you define the populations inside the sludge and you work with that. Then you can go one step further. You can describe the metabolism of the organism. You can describe the metabolic routes inside the organisms. You even make it more and more a wide model. You describe more and more in detail what's going on. And the trick is, of course, for each process to figure out what is the adequate level of description. If you make a more complicated description, do you get also a better description of the wastewater treatment plant? Now, for instance, as we will see later, for nitrification, you can do that, but you will not gain much extra with that. Whereas, for instance, for phosphate removal, you will gain by including metabolic description. So the level of black box versus white box modeling depends on the purpose and on what you want to do with that. And of course you can go even in more detail, because you can include genetics, you can include genetic change and all these kind of things. Technically, in principle, no problem, but again, what is the purpose and to what level are you going to describe? And if you make your model too complex, there's too many parameters for what you want to describe in the end, then you're just spending a lot of time and a lot of effort on a further bit senseless project. So realizing at what level you have to be between pure black box and pure white box, ab initio modeling, so to say, that depends again on the topic, and it's not that one of these approaches is good and the other is bad. It depends on the purpose, and that's something you all the time have to keep in mind, because that's where modeling often goes wrong. And people neglect the purpose and the model becomes the purpose, and then it's not a maybe academically sometimes an interesting issue, but you don't learn anything anymore. So, what is a model? And as I said already, and want to emphasize that once more, is that the model should always be just relative on the purpose of its use. That's model is never made for the model itself. There's also no absolute need that a model is exactly describing reality. It depends again on the purpose. And what do you want to do with that? And if you make a model, you for instance have an idea about say N2O emissions from wastewater treatment plants, you can come up with maybe 3 or 4 theories. And what you can do is just put the theories in a model, look how the different models describe what are the trends. Will they go up or down? And how do the trends compare to reality? At that moment, the only thing you're interested in is do the hypothesis generate a model which gives the correct trends. At that moment, you don't need a good calibration. So if you're interested in trends and only are interested in will things improve or decrease, quite often you don't need very exact calibration of a model, exact knowledge on the parameter values. You need a rough knowledge on the parameter values. But of course, if you have to predict that if legislation says that every sample you take from the effluent should be below 1 milligram ammonia per liter, the accuracy of the parameters you put in the model should be much higher, because then you have to guarantee that you can predict this 1 milligram exactly. So again, the purpose of the model defines how accurate the parameters which you use in the model should be. An important reason to model is that it forces you to make everything explicit. Very often you will see in papers or in what people describe is something is better, something is larger, or something is smaller, or something is higher, but that doesn't tell you a lot, because that's whether something is smaller or larger depends on the perception of the researcher. A person working with full-scale plants has a different perception of large compared to someone who works in the lab, for instance. So, and it only becomes important to really quantify the size, quantify the rates, quantify the conversions at the moment that you model, because then you have to fill in numbers. You cannot fill in, well, this is a large you cannot fill in this is a high concentration or this is a low temperature. No, you have to fill in that the temperature is 15 degrees Celsius. So you're forced to become quantitative and you are forced to become objective. And in that way, process knowledge get better constrained. Of course, you can do this without modeling, but very often by making a model you get a framework which takes everything into account which is relevant. So it helps you to organize and define. And the second point is that modeling quite often can save time and money. If you can compare things in a quantitative way instead of in a more qualitative way, you can much more easily take decisions. If you know that there's 2% difference, you easier take a decision than when you know that it's more. 2% is also more, but if it's more, it can be 2% more, it can be 20% more. You don't know exactly, and if you don't quantify in discussions, this will remain an open question and takes usually a lot of time. The third is decrease of risk. You can decrease risks, especially in decisions, because you can evaluate with models what will happen if. So you can get an idea what will happen if the flow rate doubles. What's the effect on the effluent concentration? Or what will happen if this or that happens? So you know up front, again in a quantitative way, what the effect is of potential risks. It's not, again, a qualitative risk, a kind of black box risk, but you quantify it, and that helps a lot because then you know which risks you will take and which risks you won't like to take. And you can take upfront measures to prevent or to make measures that if this risk occur, that they are controlled. A fourth point of relevance is the improved knowledge transfer and decision making. And especially wastewater treatment or environmental engineering in general is important there because you deal with all kinds of different disciplines, microbiology, physical engineering, biological engineering, mechanics, operators, engineers, scientists. Everybody has their own way of looking to things. By phrasing things in a mathematical context, we use more or less, say, the same language. And that helps to communicate and also to ask to different disciplines what they should deliver. So in a model you need a growth rate and a yield. So a microbiologist should not only tell you that he has a nitrifier, but should also tell you that what the growth yield is and what the growth rate is, and preferentially what the affinity constants are. So by having a model, you know which questions to ask to the other discipline to solve. If it's going about mixing, you can ask the physical engineer, what's the mixing characteristics? And you can implement that in the model. So it's easier to communicate between fields because, again, you have to quantify and to objectivate. And also by having a uniform model, everybody speaks the same language. If you would look in the literature before Activate Sludge Model number 1 was published, you will see at least 5-6 different ways of modeling wastewater treatment plants. And sometimes nowadays in literature, people who don't use ASM1, you see also that they do it in a different way. And it becomes extremely difficult to understand what they are writing up. Because everybody has their own notation, their own way of dealing things, their own way to implement equations. By having a kind of uniform context, you have a uniform language, which makes the knowledge transfer much more easy. Then, of course, a model can very efficiently be used for training, because the operator can learn what happens if he takes certain actions on the screen instead of in reality, and in that way learn quicker and also evaluate without that much risk. And in decision making, so that's more reporting to managers, etc. You can quantify. You can just say, well, okay, if you take that decision, your risk on failure of the installation is this and this. And if it's quantitative, again, it's more easy to transfer the knowledge and the information. The last point, why modeling is very important in environmental engineering or wastewater treatment especially, is that if you look to many industrial processes, you will see that in an industry, every process unit has one task. Every reactor has one conversion. If you look to wastewater treatment plant, in one reactor, you have many processes occurring at the same time. Moreover, you cannot control what's going into your process, like what you can do in industry. Flow rate is variable, the composition is variable, everything is changing all the time. If you have a normal industrial process, you control exactly the concentration, the flow rate, the pressure, the temperature, at least you have the potential to do so, but in environmental field this is not possible. So in order to deal with this dynamics, you need a model, because you cannot do that easily on the back of a envelope calculation type. You can do the design on that, but understanding the process, that's not possible. And the last part is that, of course, wastewater treatment plant is integrated. You're not treating the wastewater because you like to treat the wastewater. You're treating the wastewater because you want to have a good environmental quality, or you want to reuse the water. So it's part of a much bigger system, and you want to link up what is happening in a wastewater treatment plant in a total system model, which describes, for instance, the sewer, the wastewater, the receiving waters, etc., so that you can take decisions, that people at, say, a higher level can take decisions on what is best, invest in a sewer or a treatment plant, or optimizing the receiving waters in one way or another. How do these interact with each other? And again, you need to do this in a quantitative way, because otherwise you cannot make a sensible decision. So where are models used in wastewater treatment? Well, and now I speak more from my experience, what I see from the field in the Netherlands. A very important part, and this might seem strange, is people learn a lot by making a model from that treatment plant. You might think that an operator understands and knows this treatment plant, but very often you will discover that during a modeling exercise, because you have to objectivate and quantify what you're doing, they will find out things about their treatment plant they did not realize, they didn't know before. This can be valves which are wrong, this can be aeration systems which are not well operated, pumping flow rates which are different. All kinds of things are different than what you get from primarily data. The second main point where it's used for is especially scenario analysis. So you have to take decisions, because if you have to upgrade a treatment plant, a typical trajectory will take a few years before, after you start thinking about it, it's really upgraded. But you like to postpone a decision for upgrading as long as possible. So you can look for scenarios. Well, what is the risk if I postpone it for 1 or 2 years? Or if you have different options for upgrading, which one is the best, or are they really different? Then quite often they are used in new plant design. Models are not used for designing treatment plants. Well, not at least dynamic models. People use a static model for the primary design, but then once you have the primary design, you can check whether with the local variation of, for instance, the hydraulics, this design can be improved or can be gained on certain aspects. And lastly, models are then used for management decision, as management decision tool, and for developing control schemes. The last part is, if you look in, say, water research, water science technology, sometimes you might think that models are mainly used for control, but in reality they are not that often used for control or building controllers. They are much more used for scenario analysis, etc. in practice. But that's much less interesting to publish for in the scientific literature. So the last point here is going through these points a little bit quick again. Just getting insight in plant performance, that's really a big thing. And that, why do you get that insight? Because you have to quantify, you cannot just deal with it anymore. And a model is based on mass balances, which means that if your mass balance over a treatment plant in the measurement is wrong, also your model will be wrong. So you are forced to look at it, and you can use mass balances to detect errors and do data reconciliation. And you will very often find that the primary data are not correct, pump flow rates are different, etc. And by applying these tools, which goes a little bit too far for this lecture now, we can improve that. Then we can evaluate these possible scenarios for upgrading. In this case, there's no need for extensive calibration, because you look to the future, and in the future you anyway have already a big uncertainty on what the real flow rate is in 5 to 10 years, what the real loading rate is. And that uncertainty is often much larger than the uncertainty you might have in the growth rate of a nitrifying bacteria. So there's not really a big need for that calibration, because the uncertainty in the model is in the input and not in the parameters. you can very easily then use the trends. Will one measure have more impact than the other? Because that will be good enough. And forget about small differences, because they're not relevant, because within all the uncertainty towards the future, small differences fall away in the uncertainty range. For evaluating a new plant design, again, we are dealing with uncertainties. You design a plant, it's built 5 years later, it's operated, and it will operate for another 15 years at least. So you have to make a design for how the plant works in 20 years. A lot of things have changed. There's a lot of uncertainty there. Again, don't try to make a too correct model for this kind of exercises. But you can use a dynamic model very well for testing for sensitivities, what is sensitive in your design, and for redundancies. Typically, most of the static design protocols which are available in practice, there's a lot of safety factors. Because if you have a standardized protocol for designing a wastewater treatment plant, like in Germany, then that treatment plant, that design has to be made for the most worst treatment plant in Germany, because all treatment plants should work well, so even the one which in the most worst condition. So which means that almost all other treatment plants will have a bit too high safety margin. And you can get rid of that redundancy, make smaller systems. In this way you can evaluate whether with the local conditions, the local variations, etc., how it works out. Models in support and management decisions is mainly making them more objective. So you can tell a manager, this is the risk, 20% failure, 50% failure, and he can take a more easy decision than, well, the risk of failure will increase. That's a too general trend to really make a decision. And you get insight in real difference, because if in one case it's 5% increase, and the other case it's 7% increase, of course one is better as the other, but the difference is very small. So it's not the reason to decide probably on one or the other. Then the control schemes, they are effectively in reality never really direct model-based controllers applied, although there's a lot of research going into that. But what is happening in practice more and more is that simple controllers are even tuned. So it's setting a PID controller, the set points, etc., and the regulation of the PID controller based on the model, and then transfer the controller directly into the controller at the treatment plant, and in this way have a much quicker introduction of new control scheme at a treatment plant, where typically in the past the optimization of the controller would be done at the site, and that's of course much more difficult testing than on a model, because the treatment plant will have to keep working well. And it takes of course a lot of time before you get a response back, because if you change the controller structure you have to wait half or one retention time in order to see whether it has effect, whereas in a model you can do the simulation very quick and you can see the effect.